Hello everyone, my name is Jason Gregerson. In this video we're going to talk about the Gram-Schmidt process. So first, what is the Gram-Schmidt process? The Gram-Schmidt process is a process that allows us to take a regular basis, u1, u2, out to up, of some vector space W, and generate an orthogonal basis, v1, v2, dot, 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 to vv, for W. So we're taking a regular basis and we're creating an orthogonal basis. So we've already seen some smaller examples of how we could possibly do this. For instance, if we have two vectors in R2, we know that these two vectors u and v are linearly independent, they would form a basis for R2. And I can see geometrically here that these two vectors are linearly independent because they're not multiples of each other. Now if I want to take these two basis vectors and find an orthogonal basis, well, I could project u onto v to find this vector. That'd be my projection vector. And from there I could take u minus my projection vector to get this vector. And that vector would be perpendicular to v. And so if I looked at this projection vector and v, that would form an orthogonal basis. So that's the big idea behind the Gram-Schmidt process. Now, of course, we want to generalize this to larger spaces, some Rn spaces, and see what that process looks like there. So let's look at this Gram-Schmidt process in R3. So if we are given a basis for R3, our goal is to find an orthogonal basis, these v vectors, for R3. So we'll start by just choosing one of our vectors. We're going to let v1 just equal to u1. That just gives us a starting point. There is our first vector, v1. So from now we have to find a vector v2 to form our basis where v2 is perpendicular or orthogonal to v1. So to find that, we're going to use u2 to find our v2. We're going to take the projection of u2 onto v1. And then we'll find this vector, which is u2 minus the projection of u2 onto v1. And that should be our next vector, v2. So v2 is going to be our u2 vector minus the projection of u2 onto our v1 vector. And so we can see that would give us our v2. So we will call this thing v2. I'll draw it back over here. So now I have v1 and v2. I have to find my third vector that's orthogonal to both v1 and v2. So to do that, I'm going to use u3 and the space spanned by v1 and v2 to find my v3. And I'm going to project u3 onto this subspace, just like I've done before. So in other words, I want to project u3 down onto this subspace, and then take this vector, which should be u3 minus the projection of u3 onto the span of v1 and v2. Now how do I calculate that projection? So v3 is going to be u3 minus, well, if I look at the projection of u3 onto that vector space, that just looks like the projection of u3 onto v1 plus the projection of u3 onto v2. Now if I just distribute my negative sign, I have u3 minus the projection of u3 onto v1 minus the projection of u3 onto v2. All vectors here. And so this would be my formula for v3. And so now we have our last vector v3, and we can form our orthogonal basis. Now, of course, if this was a larger space and we had to keep going, in other words, if we had a four-dimensional subspace W, where we had u1, u2, u3, and u4, and also we wanted to find four v vectors to form the orthogonal basis, we would just keep following the same pattern. So in other words, the v4 vector would just look like u4 minus the projection of u4 onto v1 minus the projection of u4 onto v2 minus the projection of u4 onto v3. And we could just keep going on with this larger process for larger spaces. Let's look at one example. So we want to use Gram-Schmidt, and we have a space W, which is the span of these three vectors, so these would be a basis for our space, and we want to find orthogonal basis for the same space. And we can see by looking at the dot product between these two vectors, so for instance if I take this dot product between these two, I will get the value of 1, not 0, so these are not orthogonal as is. I'm going to call these vectors u1, u2, and u3. Once again, my goal is to find an orthogonal set of vectors v1, v2, v3 that's a basis for W. So we'll start off. v1 is just equal to u1. So that's our first vector. v2 should be equal to u2 minus the projection of u2 onto v1. So this is u2, which is 1, 2, 0, 0, minus, and now here's our definition of a projection again, that's u2 dot v1 over v1 dot v1 times our vector v1. So this is 1, 2, 0, 0. Now the dot product of u2 and v1 is going to be 1 plus 0 plus 0 plus 0. And then v1 dot v1 is going to be 1 plus 0 plus 1 plus 0. So that's 2. And this is times the vector v1, 1, 0, 1, 0. So it looks like I have 1 minus a half is a half. 2 minus 0 is 2. 0 minus a half is negative 1 half. And I have 0 for my last component. And so this would be my vector v2. Now I have v1, I have v2. Lastly, I have to find v3. v3, as our definition states, is u3 minus the projection of u3 onto first v1, and then minus the projection of u3 onto v2. Make sure you're projecting onto our new orthogonal basis, not onto our u vectors. So these are projecting onto v1 and then v2, not u1 and u2. All right, so what's u3? 0, 10, 4, and 1. Then we have the projection of u3 onto v1. So once again, u3 dot v1, v1 dot v1 times v1 minus the projection of u3 onto v2. So I have u3 dot v2, v2 dot v2 times the vector v2. 0, 10, 4, 1. Now we'll start doing some of these dot products. I have u3 dotted with v1. Looks like I am taking that to be 0 plus 0 plus 4 plus 0. So I have a value of 4. v1 dot v1 is going to be once again 2 times my vector v1 minus, now I have u3 dot v2. So u3 dot v2 should give me 0 plus 20 minus 2 plus 0 all over v2 dot v2, which should be 1/4 plus 4 plus 1/4 times the vector v2, which is 1/2, 2, negative 1/2, and 0. All right, starting to look a little ugly. Once again, we'll just go through these calculations. So I have 0, 10, 4, 1. Minus 2 times this vector, so it looks like 2, 0, 2, 0. Minus, now I'll do some simplification over here. This thing looks like 18 divided by 4.5. So 4.5 is 9 halves. Instead of dividing by a fraction, I'll flip and multiply. So I will get 36 ninths, which is equal to 4. And so if this value is just 4 and I multiply it by this vector, looks like my result will be 2, 8, negative 2, and 0. All right, now I'll just subtract these vectors. I get 0 minus 2 is minus 4. I get 10 minus 0 minus 8 is 2. 4 minus 2 plus 2 is 4. And 1 minus 0 is 1. So this would be my vector v3. So now I have v1, v2, and v3. So I have my basis V1 is this. V2 is 1/2, 2, negative 1/2, and 0. And my last vector is negative 4, 2, 4, and 1. So this should be my orthogonal basis. Of course, the best way to check to see if we've actually done this correctly is to look at some of the pieces here. If I take this dot product, I'll get 1/2 minus 1/2, which is 0. So they're orthogonal. If I look at the dot product of these two, I'll get negative 4 plus 4, which is 0. So those are orthogonal. And lastly, what about these two? If I take this dot product, I would get negative 2 plus 4 minus 2. Once again, that's equal to 0. That's orthogonal. So I really do now have an orthogonal basis for my space W. Now the last question we'll ask real quickly is, does it matter if I scale my basis vectors? So I have my new basis, my new V1, V2, and V3. And if I took V1 and multiplied it by 2, for instance, would that still span the same space? It would. So are they still a basis? Yes, even if I scale them. Are they still orthogonal? Well, if V1 dot V2 is equal to 0, then 2 times V1 dot V2 is also equal to 0, because I have the associative property of scalar multiplication here, so I can just do that product first, and then 2 times 0 is just 0. So yes, they will still be orthogonal. So I can scale these things and not change the fact that they're orthogonal basis. Now why would I want to do that? Because I can also create an orthonormal basis now. Now that I see that I can use Gram-Schmidt to find an orthogonal basis, if I just take my basis vectors and normalize them by dividing them each by their length, then not only will they be orthogonal, but they will also be unit vectors. And so it would be easy enough for me to go from my orthogonal basis to my orthonormal basis. Alright, so now we've seen in this video how to take a regular basis for a vector space and use the Gram-Schmidt process to generate an orthogonal, or if we choose, an orthonormal basis for a vector space. And that concludes this video. Thank you.